Hello everyone. In the previous video, I talked about one or two examples of permutation. I talked a little bit about multiplication principle. Let us extend the problem of permutation now. And here there is a little different type of problems in which I have to again select R things out of n dissimilar things. But the condition is that a particular thing is to be always included in each arrangement. Let's understand through an example. Let us suppose a kid has certain toys with him. He has a bus toy, he has a toy of car, and he probably, let's say, has a toy of I don't know, probably a drum, and he has another toy which is a gun, and he has another toy which is. So I'm going to write one toy in different color with a purpose, and there is another toy, let's say, and that particular toy is something called teddy bear, let's say, right? So if you see, this particular boy has certain number of toys, one, two, three, four, five. So he has, if I have to notify it, he has n toys, and here it is given by five. And let us assume that he has to select three toys out of which is given by R. And the condition is that in whenever he selects three toys, doesn't matter how many possible ways he selects, his teddy bear is supposed to be there each time. So let's see, and let us extend the problem. What is going to happen? Doesn't matter what actually a boy actually has to select. So I'm going to write a selection here. So he's selecting here, let's say, and one space is occupied, teddy bear. That's it. Now I'm left with two places, and actually how many objects I'm left to choose with. Now I have two more toys to choose. So I'm going to again pick a different color, let's say. So I have two more toys to choose, right? And these two toys, so I have two more places left. That means if I look into R, then I have R minus 1 places left. R minus 1 toys to choose. Out of how many toys? Out of n minus 1 toys, because TB, teddy bear, has already been selected. So I am left with these total number of toys available with me. So I have to select R minus 1 toys out of n minus 1, which is in this case is 4 toys. So now this could be anything. So how I can make these two selections? I have a freedom. So I can make these selections out of total 4 left out choices, and two choices I can make for C2. And one is already there, right? One is already there. That teddy bear is already there in each selection. So that is one particular way with how this particular problem can be solved. Teddy bear is occupying place number one. Same way, teddy bear can occupy place number two, and teddy bear can occupy place number three. So that means teddy bear can actually occupy three different places. That means here, here, and here, right? So it can also occupy three different places in this total arrangement. So if I look into this particular problem, these are the total possible arrangements I can take up. 3 times 4C2. So if I write it in a generalized format, if there are n objects out of which r selections has to be made, and one object is fixed, or to be selected every time, then the total number of possible permutations which can be collected are, or can be given by, r times n minus 1 p of r minus 1. That's exactly how the total particular permutations can be given. And this is a very, very important concept which we will be using in the problems to come. Let us have some more examples actually, or some more important conventions. And here I am trying to find out the number of permutations of R things chosen out of n dissimilar things when a particular thing is to be always excluded. So in the previous slide, I was including the particular thing, and this time I am always excluding the particular thing. So now the problem becomes very, very simple. That means if I go to the previous one once again, and I'm saying teddy bear is never to be selected. So fundamentally, I'm left with a simple concept of that there are n minus 1 objects which are left now. That means instead of n, that means n minus 1 objects are left, and I have to select R out of them, because still I have to select 3 toys out of 4 now, because teddy bear is out of equation. So if I have to exclude one particular thing at every point of time, then I'm left with one object less and the selections are same. So you can differentiate it, and this particular problem is when one thing or has to be included every time, and this is where when it is to be excluded every time. So this is the differentiator, and there is a change here in the formula. You can see that easily, and I think you can understand the reason logic here, how these things are going to do. So I'm going to rewrite this particular thing here. It will come out to be n minus 1 PR in terms of exclusion. Let's have a very small proof, and let us understand how this small simple things of permutation actually works. So if I see, then I have something like that if I exclude a particular thing and if I include a particular thing, then these total permutations are going to come as a complete permutation. So let us understand thing, and by the permutation formula, you can easily understand that this can be rewritten as n minus 1 factorial divided by n minus 1 minus r factorial. So that is what it is going to be, and this is going to be r times n minus 1 factorial divided by, it is going to be n minus 1 minus r minus 1 factorial. I'm going to put it into double bracket and see exactly how this thing is going to work. So if I release the bracket on this particular side, so it is going to be something like this. You can simply write it n minus 1 factorial divided by n minus r minus 1 factorial. Just rearrange the term, nothing else, and it is going to be r times n minus 1 factorial divided by, and if I open the bracket, it is going to be minus 1 minus r plus 1 factorial, which is going to cancel out. And I'm left with n minus r factorial here. So n minus 1 factorial divided by n minus r minus 1 factorial. And if you see this, this is r times n minus 1 factorial divided by, if you see, this is remaining n minus r factorial. And how you can write it, you can write it simply like this, n minus r minus 1 factorial. And it is very easy to understand, you've got like factorial n can be written as n times n minus 1 factorial. So if you've got something like n minus r factorial, that can be written as n minus r times n minus r minus 1 factorial. So now I can see what I can take common out simply. So if you see, this whole term is absolutely same as this much. So I'm going to take it common out. And now I'm to left with n minus 1 factorial divided by n minus r minus 1 factorial. And within the bracket, I'm left out with 1 plus r upon n minus r. So if you solve the bracket, so you're going to get n upon n minus r definitely. And if you solve this entire thing out, a little arithmetic, you're going to get n factorial upon n minus r factorial, which is actually npr. So that's the right hand side. Sorry, left hand side. So you have selected the. So this is a simple proof when exclusion and inclusion actually results, the total results exactly into the complete permutation. Now this is again a very important concept in permutation when you have to find the number of ways in which n things may be arranged among themselves, taken all at a time, when p things are of one kind and q of second kind and r of third kind. Then how the different possibilities of permutation can be combined or can be calculated. In that case, it is definitely going to go divide Pn factorial divided by P factorial, Q factorial, and R factorial. And I'm going to explain it through some practical example, how exactly the entire thing works, how we can go ahead with these kind of problems where there are some similar things. So we'll be going through a practical example and understanding it. Let us see the first problem. And in this problem, if we see, then I have something like in how many ways or how many numbers lying between 10 and 100 that can be formed with the help of digits 3, 0, 4, 5, 6. So if I see how many numbers lying between 10 and 100. So between 10 and 100, what are the numbers? 11, 12, and so on. All these are two-digit numbers, right? All these are two-digit numbers. And there are how many digits that have been given to me? 5 digits, 3, 0, 4, 5, 6. So actually the problem is that I have to see there are 5 digits, out of which I have to select 2 to form a number. So look at this. So the total possible numbers, and these can be given by simply 5p2, and if you solve it, it's going to be 5 factorial divided by 5 minus 2 factorial, and that's 5 factorial divided by 3 factorial, and that is 5 times 4 times 3 factorial divided by 3 factorial, and that gives you 20. 3 cancels out. But you see, out of these, there are certain numbers which, if I see these particular things, there'll be certain numbers which will be formed like 03, 04, 05, 06. These numbers are less than 10 and they are not between 10 and 100, right? So out of 20, 1, 2, 3, 4, these 4 numbers need to be removed. So total possible numbers between 10 and 100 are given by 20 minus 4. So I've removed these 4 possibilities and means 16. Next video I'll be doing more questions on permutations. Thank you.